So the dual is feasible, but then you are going to have a different change in primal and dual. So the delta dual this time is going to be lambda, and then delta primal would be equal to b times x over b plus b times, it's the same formula, just replace c with the new number, right? Plus 1 minus x. So it's going to be 1 plus 1 over c minus 1. So it is again equal to c over c minus 1, but c this time is equal to e to the power 1 over lambda. It's going to be e to the power 1 over lambda divided by e to the power 1 over lambda minus 1. What matters for convective ratio is the change in the primal divided by the change in the dual. This quantity is upper bounded by 1 over lambda times e to the power 1 over lambda divided by e to the power 1 over lambda minus 1. And I leave this as an exercise that this number here is in fact smaller than the other number that we have, which is 1 over
1 minus
e to the power lambda minus 1, or equivalent to e to the power minus lambda divided by 1 minus 1 minus lambda. This is actually true for every lambda between 0 and 1.
The other number was e to the power lambda over e to the power lambda minus 1.
Let me finish this. It's the same thing.
No, it should be e to the power lambda over e to the power lambda minus 1.
The other number was
E to the power lambda over e to the power.
Which is 1 over 1 minus e to the power 1. But this is again something that the person who described it should prove. Okay, so this is the proof of robustness, and I didn't emphasize on it that much because this is exactly the previous proof that we saw for a experimental problem, but modified by this change in the parameters. But now the part that is slightly different is the robustness proof, is a consistency proof. The consistency. Yes.
Why? What? Isn't it the same that as what we had? I think you said
this expression?
No,
yeah. No, so it is upper bounded by that. So therefore, case number 2 is not the bottleneck. Case number 1 is going to be the one that is bottleneck. Therefore, that would be the number you get for us. All right. So consistency. Let's think about it. I'm considering again 2 cases. So case number 1, if the number of prediction, let's say, is larger than, in this case, the predictor is going to buy, right? Because the prediction number is larger than this, so the predictor is going to buy. But then, so predictor is going to buy. And therefore, the cost of following prediction is equal to. Okay, good. Now I have a question. If this is the case, we are going to go with large objects, right? Meaning that we will use So if this is the case, just as a recap, so we are gonna use C equal to e to the power lambda and C prime equal to 1. When I say you go with the large update, that means that every time the initial value that x starts with is going to be a larger number, therefore you're going to converge faster to 1. So there is more, algorithm is more aggressive towards binding. In that case, how many updates do we need to do in the primal? So as a recap in the previous analysis, so the delta primal in each step is always equal to delta primal in each step is equal to C over C minus 1, which is for the case when C is equal to e to the power lambda is e to the power lambda divided by e to the power lambda minus 1. And then how many iterations do we need until we stop binding? We calculate that.
Lambda b.
Right, so here, basic summation of yi was an indicator for how many steps you want to go. This is that case, right? So we also know that in this case, summation yi is actually at most lambda b. Therefore, number of steps to update is actually at most lambda b. So the combination of the two says that also the primal at the end is going to be at most lambda b times e to the power lambda divided by e to the power lambda minus 1, which is equal to lambda times the cost of following the prediction. Lambda divided by 1 minus e to the power minus lambda times the cost of following the prediction. Okay, so this is the first case, checks. Case number 2. Imagine the n of prediction is smaller or equal to b. In that case, we go with the large update. So we go with the small update. So C is going to be equal to e to the power 1 over lambda. C prime is going to be equal to lambda. Let's do the same calculation. So first of all, if this is the case, then the predictor is just gonna rent, right? And the performance of the predictor really depends on how many number of days you have. So predictor is going to rent. Therefore, the cost of following the prediction is essentially equal to n, the number of days. So what about our algorithm? So our algorithm is going to do this update. Let's do the following. So the delta primal in each step, I claim it is at most C over C minus 1 with the new C, which is equal to e to the power 1 over lambda divided by e to the power 1 over lambda minus 1. That's the upper bound of the, it's actually equal, right? So it's a, let's do the upper bound. So I'm going to increase the primal until either escapism finishes early or I hit 1. Therefore, I can say the delta primal initial step is at most this number, meaning that if I'm still in a normal period where I'm increasing x, I haven't hit 1, and the ski season continues, then the delta primal is going to be equal to this number. And the moment that the ski season finishes, then delta primal becomes 0 because you don't change primal anymore. Does it make sense? What I'm saying? The delta primal, if you look at that continuous process in the algorithm, is always equal to this unless a ski season ends. Yes.
The steps are days.
The steps are days, correct. Yeah. Primal initial step, I mean the delta primal each day. If this day is part of the ski season, then the delta primal is going to be exactly equal to this. Unless x has hit 1, and in that case, it's going to be 0. And if you're looking at the day that is after the ski season, then delta primal obviously is equal to 0. So then this is just an overlap. What I'm trying to say is that as a result, I can always say the total primal is at most n times this one. Because if you're outside of the ski season, this is 0. Up to n point, at most you get this change in the primal, therefore your total primal is going to be at most. And because of the fact that the cost of following the prediction in this case is equal to n, this is going to be at most e to the power 1 over lambda divided by e to the power 1 over lambda minus 1 times the cost of following the prediction. Okay, so now which case is binding? There was this inequality there. Let me write the inequality. So algebraic lemma. And it needs a proof definitely, but I keep it as just an algebraic lemma in the lecture. So algebraic lemma is that
Lambda times E1 over E2.
right, like 1 over lambda times e to the power 1 over lambda divided by e to the power 1 over lambda minus 1 is at most lambda over, 1 over 1 minus e to the power minus lambda. This is exactly the lemma that we need to say that case number 1 is binding when we're doing the robustness proof. And using the same lemma, you can see, well, so this comparative ratio here with respect to the predictor is now smaller than this comparative ratio. It's exactly the same comparison. This time, case 1 is going to be binding.
So in both cases, case 1 is
Right.
fine.
One thing I'm confused by is this ML predictor you have. This is like acting irrationally again here. I think this has been my confusion. So when n pred is less than equals to p, we say that the predictor is going to rent always, and it gets a cost of n. But it's an irrational behavior in a scenario when like n
You
is
mean
bigger
the
than
predictor is doing something rational?
irrational.
Sure. I mean, you can change the prediction by saying that, hey, so if S cases and n that don't rent, how do you want to fix that?
So I want to have it such that it has cost min of n comma b.
How would you define your predictor?
So you follow your n predictor. So in this case, when n pred is less than equals to b, you follow it until n pred, and then you realize that okay, your n pred was wrong, but you still keep following it until b. But then after b, all bets are off. You're like really wrong. You should just buy it at this point.
Sure, I guess the idea is really not trying to design a predictor that itself is trying to be competitive.
But we are
So you wanna push all the competitiveness against worst case input in the algorithm and assume that the predictor is as simple as possible, is only relying on the signal. Again, this is an engineering view towards online algorithm. It's not really trying to design the best algorithm given this advice, right? So first of all, when you get the advice, you have to define this notion of following the prediction. And there you try to say, I try to be as naive as possible, but use the prediction. And then the most naive way of using a prediction is really saying that if n of prediction is larger than b, I'm gonna always buy, otherwise I'm gonna rent.
You could imagine like some algorithm who start doing MPC and it sort of doesn't look at the sum cost. It says, oh, going forward, what's my cost? And if it going forward thinks it's going to snow for less than b days, it'll just keep saying rent. So it still makes sense in an MPP world that you could just say keep rent. In a competitive cell, it doesn't make sense. So
yeah, if the input is adversarial, really can't do anything with this prediction. I mean, definitely you can say, hey, I try to have an algorithm that is a little bit robust and also uses a prediction, then this is exactly what you want to do at the first place. You don't want to include that in your definition of following advice.
Why is it ML advice? Are there applications where the advice is by learning algorithm, or this application is like non-ML advice, it seems, or just generic advice?
I mean, the question is how do you get this NPRED? And maybe you have looked at the data in the past and from that you estimated the length of the cases.
So there are other applications where.
Yeah, actually, speaking of which, let me finish the class by telling you a little bit about the Adwords problem. I just want to mention what does prediction in this context mean, and definitely look at this paper. So the problem is Adwords, as we always have been teaching. Queries arrive to advertisers, you want to match the queries to advertisers. And then we looked at this balance algorithm or the Adwords algorithm where you match the arriving query to the advertiser that has the maximum Bij times 1 minus some G function of the normalized spent budget, right? Now, imagine in the same setting, there is also a recommendation algorithm. Meaning that every time that a query arrives, the recommendation algorithm is recommending you to match the query to some advertiser. And also, you know that following the recommendation at all times is going to be feasible, meaning that none of the advertisers' budget is going to be exhausted. So you know this about the prediction. And now the question is, can you design an Adwords algorithm, an online algorithm that is, again, R lambda robust and C lambda consistent? And this paper finds the R lambda, C lambda, which is again information theoretically optima, similar to the one here. I didn't show you why this is information theoretically optima, but it is. And one open problem that, I mean, maybe it's not open, but it's kind of like a question I have in mind is there a Primal-dual based proof for the performance of this ML advice on the number? Because for the Adwords, you have this beautiful Primal-dual proof. If you look at this paper, it is relying on a direct proof of the performance of the Adwords algorithm. Because in the original MSCV paper, meta summary Razioni paper that showed the 1 minus 1 very competitive for Adwords, the proof wasn't Primal-dual. It was a direct proof that was using a technique called factor revealing linear program. And then this old paper, which has come a little bit after that paper, is actually building on top of that technique and gives you the optimal trade-off between R lambda, C lambda. For the experimental problem, the story is kind of the same. There is an older paper that gets exactly the same R lambda, C lambda using a non-Primal-dual proof. And what we covered today was a kind of a nicer Primal-dual proof of the same thing. Now I'm wondering if there exists a Primal-dual proof to show the result of this paper. And there is a good reason for that, because if there is such a result, it can be extended to a couple of other settings that are heavily relying on the Primal-dual analysis.
So the algorithm, does it look like Primal-dual? Like, this is an algorithm that looks Primal-dual.
Yeah, so the algorithm is not Primal-dual. it's pretty similar to Adwords. So basically what it does, you can actually write down what the algorithm does. It's very similar to the original Adwords. So suppose query, let's say I arrives. Now, J hat is what is recommended by the prediction. And lambda is your trust parameter. So what they do is that if lambda, so if lambda times 1 minus, so lambda times bi j hat times 1 minus g lambda, and g lambda is a function we define. G lambda of the normalized budget of advertisers that you have by j hat divided by bj hat. Is greater or equal to Eij times 1 minus g lambda of j divided by bj, then follow the advice. For every j. Otherwise, pick J star, which is the argmax of Eij times 1 minus g lambda by j divided by bj. And here, think of lambda to be 1 minus lambda. So if lambda is equal to 1, you have the maximum trust in your prediction. If lambda is equal to 0, you have the minimum trust. So essentially, it says that, so if let's say lambda is equal to 0, that means that you have no trust in the prediction, then you never actually follow the recommendation, and you always pick the J star that maximizes the modified bit with the estimated shadow price. But then if you have the prediction, you trust on the prediction. If it can beat that bit, then follow that one. And G function this time is following, it is using lambda, so it is e to the power lambda x minus 1, rather than e to the power x minus 1, that we have always used. But you should take a look at the paper carefully to make sure. Yes. Excuse me, so it is e to the power lambda times x minus 1.
So it's exactly g to the power lambda.
What's that?
It's exactly g to the power lambda.
Right, it's the previous g to the power lambda. Yeah, okay. I could actually use g to the power.
I initially thought that.
Yeah. Yes.
If we put j equal to j hat, that inequality will never be satisfied.
I have j equal to j hat.
So I'm looking for j not equal to, because I'm predicting j hat anyway, so any other thing that you would think.
Can you say alpha is 1 over lambda, or
Maybe you should put lambda on the other side.
oh, so they have okay. Oh, all right. So this is good. So right. So they have an alpha parameter which is 1 over lambda. 1 minus lambda.
Yeah, lambda is on the other
So
side.
basically, if and now lambda equal to 0 means that you have 100 trust in your prediction. Exactly. Good catch.
So this looks like a Primal-dual algorithm, right? Because of the dual function, but somehow.
It does, and even right. They don't have a Primal-dual proof for that. But at some point in the paper, they suggest a dual update, but they never use that. And the dual update doesn't exist in the conference version of the paper. If you look at the transactional algorithm, the journal version of the paper, they have a paragraph in which they say, hey, it seems this is similar to this particular dual update on the offline side, but then they never say what to do with that.
It's in the dual space of the content version.
Basically, if someone asks you, hey, what you're doing in the Adwords problem doesn't seem to be that much making sense because in many applications there is a recommendation, then this is going to be your answer, how to incorporate that recommendation. That, you know, hey, I'm going to actually look at J hat, the one that is recommended by the prediction algorithm, but then I'm going to discount, I'm going to intensify its effect by 1 over lambda. If lambda is smaller than 1, that means I'm giving like more weight to that particular recommendation. And I put it in competition with the other advertisers.
So the tricky bit I find with these kind of things is that you'll assume that the ML algorithm adapts to your current decisions. You should look at the remaining budget. So here you're assuming the ML algorithm just fixes the recommendations without sort of seeing the instance. Right? So that seems a little weird. But
You mean the recommendation based on the decision of the algorithm changes?
should change because the algorithm may exhaust budget faster than the algorithm predictor had in mind or something.
Right. No, that's true. That's true. This is why, for example, if the algorithm has exhausted the budget of this particular recommendation, then you never actually go with the recommendation. Yeah,
It's interesting.
no, that's a good point. Okay, so the recommendation is kind of like an offline recommendation.
Exactly. Yeah. It seems very weird to sort of think of an offline recommendation. For the entire day, I tell you for every query who you should match it to.
Yeah. But you know, in this entire literature is pretty uncharted. There are not that many papers considering hacking problems with ML advice, including online matching, Adwords, etc. The ski rental and the one that I didn't talk about, the unattraction are covering problems. There are actually a lot of examples of covering with ML advice. This paper is probably the only good paper that I know that has the hacking problem together with the machine learning. I'm sorry, I went over time. The one thing that I owe you is the correct version of the deterministic algorithm with machine learning advice and proof. I'm gonna send notes to everyone with that.